variable you create, every function you call, every object you build. They all need a home. That home is memory. Think of it like this: your computer has a temporary workspace. When your program runs, it borrows space in this workspace to store data. Numbers, strings, objects, functions, they all need a physical address in memory. And here's the thing most developers miss: where something is stored changes everything about how it behaves. Today, we explore the memory universe. Here's something that surprises many people. Your computer has no permanent thought. RAM, random access memory, is a temporary workspace. The moment you shut down, everything vanishes. Every variable, every object, every function. Gone. That's not a bug, it's the design. RAM is blazing fast, but it's volatile. Your program borrows memory while it runs, and returns it when it's done. Think of RAM as a giant futuristic storage warehouse. It's where your computer keeps everything it's actively working on. When you open a browser, load a web page, run JavaScript, all of that data lives in RAM. It's organized into addresses, like slots in a massive shelf. JavaScript divides this space into two main regions, the stack and the heap. Two completely different worlds with completely different rules. Understanding this divide is the key to understanding how JavaScript really works. The call stack is elegantly simple. It works like a tower of plates. When you call a function, a new plate, called a stack frame, is placed on top. That frame contains everything the function needs: its arguments, local variables, and where to return to when it's done. When the function finishes, its frame is removed from the top. Last in, first out. That's why it's called a stack.
Alright, we are now stepping into the real JavaScript developer workspace. This is the Visual Studio Code, one of the most popular editors used by developers around the world. Today, we are not building big applications, we are building understanding. This command may look small, but it is extremely useful. Code. Means opening the current folder inside VS Code. That represents the current directory we are standing inside the terminal. Developers use this workflow constantly because it is much faster than manually opening folders through the UI. Before running JavaScript outside the browser, we need Node.js. So, Node is a JavaScript runtime built on top of Google's V8 engine. It allows us to execute JavaScript directly on our machine without needing a browser. The next command npm stands for Node Package Manager. Think of it as an ecosystem manager for JavaScript projects. It helps developers install libraries, manage dependencies, and structure real-world applications. mkdir stands for Make Directory. A directory is simply another name for a folder. This command creates a brand new folder named Memory Lab where we will store all our JavaScript experiments and project files. cd stands for Change Directory. This command moves us from current location into the Memory Lab folder, so that all our future commands operate inside the project workspace. Now, we will reopen the Visual Studio Code directly inside our new project. Folders that all our future files and experiments stay organized inside the Memory Lab. workspace. This command initializes a node.js project, which is npm init by. It creates a package.json file. It is the heart of the JavaScript project. This file stores project metadata, dependencies, scripts, and configuration. ls stands for list. It displays all files and folders available inside the current directory. Right now, our project is minimal, only contains packages. Since this is our first JavaScript program, I am going to move a little slowly and expand every important step carefully. Later in the series, we will move much faster. Right now, the goal is not speed. The goal is understanding. So, please be here with me while we build this foundation properly. The touch command creates a brand new file instantly from the terminal. Here we are creating the stackdemo.js file, our first JavaScript experimental file. Let's rerun the ls so we can see both packages and stack.tomo.js. So, both has been successfully created inside the project. Let's understand what we are writing step by step. So, we have written function, which is a function keyword. So, function in a JavaScript is simply a reusable block of instructions. Instead of repeating the same code again and again, we place related steps inside a function and execute them whenever we need. So, function topic, we will be covering another in new chapter. So, right now we are just explaining what is function on a high level. So, here prepared copy is our main function. In series, we are calling another function name. Notice that we also have console.log statements. So, console.log is used to print messages into the terminal so that we can visually observe what the program is doing internally. Similarly, we also added one more function, boil water, and it is also as a console.log statement. And we are also adding one more function into it, print beans. The definition we are writing here. Same console.log statement. Adding one more function to it, serve coffee. And declaring the definition declaration. Another console.log statement. Finally, we are writing prepared coffee. So, if you see that all these core functions, they have been written, but they don't implicitly get called itself. So, we have to write an explicit like a method, like a declaration like prepared coffee. Otherwise, we won't able to use those functions. So once we tried this prepared coffee, there was some error fixing that. So we have written cat command. So basically cat command displaces. Let me zoom in. So cat command displays the contents of the file directly inside the terminal. This allows us to quickly inspect the entire JavaScript program without opening the return. Again, so in the next we have written the node.js command, which is execution command. So we are executing the stackdemo.js file. So node reads the file, passes the code into the V8 JavaScript engine and start executing the program line by line. This is how a JavaScript runs outside the browser environment. So, we already discussed this about this line balance execution already in the chapter 1. If you did not watch it, these two watch it. So, first prepare coffee enters the stack. Then boiling water gets pushed above. Then green beans, then finally serve coffee. One served coffee finishes, the stack frame disappears. Then green bean returns, then boil water. Then finally prepare coffee completes execution.
Let's slow down and watch exactly what happened in our coffee example. Prepare coffee calls boil water. Boil water calls grind beans. Grind beans calls serve coffee. Each call pushes a new frame onto the stack. The stack grows upward, 4 floors high. When serve coffee finishes, it pops off first. Then grind beans. Then boil water. Finally prepare coffee. The stack unwinds in reverse order. Push, 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 then pop, 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 pop. This is the heartbeat of JavaScript execution. What happens when a function calls itself forever? Each call pushes a new frame. The stack keeps growing. And growing. Until there's no more space. The engine screams, maximum call stack size exceeded. Stack overflow. The stack has a hard limit, usually around 10,000 frames. Cross that line, and your program crashes. Every recursive function needs a base case, a way to stop. This function keeps calling itself forever. Every function call adds another frame to the stack. Eventually, JavaScript runs out of stack space. Range error, maximum call stack size exceeded. This is what Stack Overflow looks like in real code. Every recursive function needs a base case. Without it, the tower collapses.
Now, let's move on to something a little dangerous. Until now, a function was calling another function. A function is calling another function. But what happens when a function starts calling itself continuously? This concept is called recursion. So let's go to the VS Code. Just like previously, let's create a function. So notice carefully inside a wake-up function. I'm calling wakeup again. Which means this function never stops itself. Every function creates another execution, And I'm using a console.log intentionally because I want us to visually observe how many times this function executes before JavaScript crashes. Let's run this through the node command. There was an error. Let's fix it. Oh, I think this was some braces. Let me see. This was missed. Yeah. So at this point, You might have already predicted the problem. So, JavaScript keeps creating new stack frames continuously. But memory is not infinite. The call stack also has limits. The moment I execute this file, and if the function keeps calling itself, and there it is, maximum call stack size exceeded. This is called Stack Overflow. JavaScript kept pushing new execution contexts into the stack until the engine could not handle any more memory. This is exactly why recursive functions must always have a stopping condition. Otherwise, the stack keeps growing forever.
The stack is just one half of the story. For simple, short-lived values, it's perfect. But what about complex objects? Arrays with thousands of elements? The stack can't handle that. We need something bigger. Welcome to the heap, a vast, unstructured memory space. Objects float freely here. No strict ordering. No floors. The engine allocates space wherever it can find room. Each object gets a memory address. When you write let user equals an object, JavaScript doesn't put that object on the stack. The stack only gets a tiny reference, a pointer. The actual object lives on the heap. It gets a memory address. The variable user doesn't contain the object itself. It contains the address to where the object lives. This is the fundamental distinction that most tutorials skip. Primitive types are the simplest building blocks. Number, string, boolean, null, undefined, symbol, big int. They live directly on the stack. When you assign a primitive to a new variable, JavaScript copies the value. Not a reference. Not a pointer. The actual value. This means primitives are completely independent. Change one, the other stays the same. B gets its own copy. Changing B does not affect A. Primitive values are completely independent. Look at the output, A is still 10, B is 50. They live in separate memory slots on the stack. No connection between them. This is how primitives work: copy the value, not the address.
Let's create one more file Previto example. Open the VS Code and also create an example. So once we create this kind of double slash, it's called single line comment. It will be useful for to know what the function does or what this variable does, so it doesn't the execution again. And also we are talking about primitive values, which are stored directly inside this memory. So JavaScript stores is 100 by inside the score1 variable. So we are creating one more variable called score2, and we are copying then the score1 copying through score2. So when we copy a primitive value, JavaScript, let's print them also. So both variable contains the same value, but they're completely independent stack in memory. Now, let's change the copied value and observe what happens. It's also print this. Ideally, changing score2 does not affect score1 because primitive copied by value, not by difference. So changing score2 does not affect the score1 because primitive values are copied by value, not difference. So primitive value stores actual values directly inside this stack memory and copying them.
This is the most important concept in JavaScript memory. When you copy a primitive, you get an independent value. When you copy a reference, you get a pointer to the same object. Primitives, isolated capsules. References, shared portals. This distinction is responsible for the majority of JavaScript bugs beginners encounter. The stack holds your variables. Some contain values directly, those are primitives. Others contain addresses, those are references. And those addresses point to objects living on the heap. The stack is a control panel. The heap is the warehouse. References are the energy beams connecting them. When you pass an object to a function, you're passing the address. The function can modify the original object. Wait. Why did user1 change 2? Because both variables point to the same object in memory. User2 equals user1 doesn't copy the object. It copies the address. Now both variables are portals to the same room. Change it through one, the other sees it instantly. This is the moment that changes how you think about JavaScript forever.
So let's start creating the one-object example file. Let's open the VS Code. Let's make some changes. So basically objects are stored differently compared to primitive values. The actual object lives inside heap memory. So for now, it's an object we won't be discussing in depth. So the variable user1 does not store the actual object. It only stores the difference pointing to the heap memory. We are going to print this. So when we copy an object, JavaScript does not create a new object. Instead, it copies the reference. Now both variables are connected to this exact same object in heap memory. Now we are trying to update it. So if whenever available changes the object, other variable also sees the updated value because both share the same reference. Notice carefully updating user2.name also changes the user1 because both variables points to the same object in heap memory. So basically objects are copied by reference, not by value. Multiple variables can point to the same object in heap memory. So we have executed that file. So yeah, you can see that we can do one more thing. We can also copy this user to also print this. So if you see here, we have like in the initial we have like. John. Now after that we got David because user 2.1 updated. So that's all about this object sharing references.
We've been creating objects, pushing frames, building references, But what happens to memory we no longer need? Objects that no variable points to anymore. Functions that finished executing. Data that served its purpose and was forgotten. In languages like C, you manually free memory. Forget to do it, memory leak. Do it twice, crash. JavaScript is different. It handles this automatically. JavaScript's garbage collector uses mark and sweep. Phase 1, mark, starting from the root, the GC traces every reference. Every reachable object gets marked as alive. Phase 2, sweep, any object that wasn't marked is unreachable. No variable points to it. So the GC destroys it and reclaims the memory. This happens automatically, in the background. You never see it. But it's always there. Even with automatic garbage collection, memory can still keep growing. How? When objects are technically still reachable, a reference exists somewhere, but you no longer actually need them. Global variables that accumulate. References that aren't cleaned up. The memory world gets overcrowded. The app slows down. This is a memory leak. We'll deeply explore specific patterns and fixes in future chapters. Most variables disappear when functions finish. But sometimes, JavaScript keeps memory alive longer than expected. Certain functions can remember values even after execution completes. This concept is called a closure. Don't worry if this feels advanced right now. We'll deeply explore closures in future chapters. For now, just know, memory can be preserved. And that power has incredible uses. Here's something to keep in your mind for later. Every time you call add_event_listener, you create a reference chain. The listener holds a reference to your callback. Your callback might hold references to component state or large data. If you forget to remove the listener, none of that memory can be freed. The fix is simple, remove event listener. But the patterns get much deeper. We'll explore event listener memory traps in detail in a future chapter. For now, just remember, add a listener, always plan to remove it. Another quick FYI. setInterval creates a timer that runs a callback repeatedly. But that callback captures variables from its scope. If the component unmounts or you navigate away, and you forgot to clear the interval, it keeps running. Every tick holds references. Memory grows. The fix? Clear interval. In React, you do this in useEffect cleanup. We'll cover timer memory traps extensively in a future chapter. For now, the rule is simple, if you start a timer, always plan to stop it. Before we wrap up, here's a quick preview of the most common memory leak patterns. Global variables that accumulate data forever. Event listeners that are never removed. Detached DOM nodes that your code still references. And timers that keep ticking in the background. Each of these is a story on its own. We'll build tools to detect them, learn to profile with Chrome DevTools, and master every fix. That's all coming in a dedicated memory leaks chapter. For now, just know these exist, and you'll be ready when we get there. Now you understand something most JavaScript developers never visualize. Every variable travels through memory. Primitives go to the stack, fast, independent, temporary. Objects go to the heap, flexible, shared, persistent. References connect them like energy beams. The garbage collector cleans up what's no longer needed. And understanding this system changes the way you write code forever. Next chapter, we go deeper into execution context, hoisting, and scope. The journey continues. You just saw where every JavaScript variable actually lives. Stack for primitives, heap for objects, references that connect them, and the garbage collector cleaning up behind the scenes. But this is only the beginning. Next episode, we go inside var, let, and constant. Why hoisting feels like time travel. Why the temporal dead zone exists. How block scope changed everything. Once you understand variables at this depth, you'll never write a buggy closure again. See you there.